Alright, today we're talking about thin film interference and interferometers. Two really fun subjects, and I happen to do interferometry for a living, so expect to hear more than you want to know about interferometers. But first, to understand all that comes next, we need to understand phase shifts when light reflects. Imagine you have some light that's striking a window or the surface of a lake. You know that some of that light transmits into the medium, but some of it reflects. Well, what happens to it when it reflects? It turns out the light can get a phase shift when it reflects. Why would that happen? Alright, so consider this, if you will. Imagine, let's go back to what we learned about waves on strings. So imagine I have a string, alright, and that string, I'm going to tie that string to a rope, a thicker rope. Alright, what happens when the wave comes and hits this junction? Well, just like when light hits a piece of glass or water, you get a reflection. Anytime the wave speed changes in the medium, you get reflections. Alright? So if I'm going from a string to a rope, remember the speed on a string is the square root of the tension over the linear mass density. So if the linear mass density gets bigger, the velocity goes down. So here is high velocity, H-I-G-H, if I can spell today, and here's low velocity. Alright, so as my wave goes from this high velocity medium to the low velocity medium, I'm going to get some reflection. Now the question is, do I get a phase change? Does the wave I send in, does the reflection come back like the wave, or does it come back like the wave upside down? Alright? Well, remember when I had my string tied to a fixed point, the wave was reflected inverted, upside down. So if I send in a sine wave, I get back an upside down sine wave. So I get a 180 degree phase shift. Alright? Well, if I take the limit as this rope gets heavier and heavier, higher and higher linear mass density, eventually it becomes a wall and I have a rope tied to a wall. Alright? So this is how you remember when I go from high velocity to low velocity, I get a 180 degree phase shift in the reflection. The transmission I never get a phase shift, but in the reflection I get a 180 degree phase shift. Well, light reflecting off of glass is similar, right? So for air I have n equals 1. Let's say my glass has an index of 1.5, whatever. So lower index means higher velocity. So I'm going from a high velocity medium to a low velocity medium. That means when I reflect off of glass, I'm going to get a 180 degree phase shift. Alright? So when the light reflects off of the surface of a piece of glass, off of water, off of a soap bubble, we get a 180 degree phase shift in the reflection. Okay? But now let's consider what happens. Our light goes through this piece of glass. Let's say it gets to the other side. When it gets to the other side, some of the light transmits out of the glass, but some of it reflects. What about this reflection right here? Now I'm going from from low velocity back into a high velocity medium. Right? What happens when you're going from low to high velocity? Well, now instead what we've got is we've got a rope. Instead of a string tied to a rope, I've got a rope tied to a string. I'm going to take the limit as that string gets infinitely thin. And the limit as that string gets infinitely thin, it's like the free end, right? Where we talked about this rope whose end could not have a derivative. So now in this limit, my thin string becomes a free end, alright? And we know when I had a free end, you did not get your reflection inverted, so there's no phase shift, 0 degree phase shift here. So no phase shift when we're going from water to air, or glass to air. Alright, so when we're going from low index to high index, the reflection gets a 180 degree phase shift. When we're going from high index to low index, it doesn't get a 180 degree phase shift. Now, if you forget which is which, you can use these analogies. If you're on a test, you can think about what happens with strings tied to a rope as that rope gets heavier and heavier, and so forth. But it turns out for what we're going to do with it, most often it doesn't matter. What matters is remembering that going from low to high is different than going from high to low index. Alright? So one of them gets a phase shift, one of them doesn't. So low end to high end, 180 degree phase shift. High end to low end, no phase shift in reflection. And once again, transmission never gets a phase shift. How do we know all this? Well, you solve the wave equation. We're not going to do that today. Alright, so imagine I have a soap film in air and it's illuminated with light near normal incidence. So here's my light ray. It's not near normal incidence the way I've drawn it. I've exaggerated the angles just so that the reflections and things aren't on top of each other. But imagine really what's happening is it's coming straight in and I'm just drawing it at an angle so I can see where all of my different rays go. Alright, so here comes my ray of light in. It hits the surface of my soap bubble. Alright, what's it going to do? Some of the light's going to reflect, some of it's going to transmit through. The light that transmits into the bubble, eventually it reaches the other side of the bubble. What does it do when it reaches this surface? Well, some of that light will transmit, some of it will reflect. Alright? Now this light that reflects, it comes back up to this first surface. What's it going to do when it gets here? Well, some of it's going to transmit, some of it's going to reflect. This light here, some of it's going to transmit, some of it's going to reflect. The light that gets up here, some of it's going to transmit, some of it's going to reflect, and so forth. And so the light that's reflected is really the sum of light that reflected here, light that did this, light that went boom, 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 and so forth. And so to calculate the electric field of my light coming out, it's just a sum. The electric field of the reflected light is just the sum of the magnitude of, the amplitude of the electric field of the light coming out is equal to the amplitude coming in times, well, I'm going to sum up each of these contributions, and each one of these guys has a different amplitude, right? Because they each time we go down here, some of the light transmits, so each one of these is going to be weaker than the last, and so that's what this thing is right here. But then they're all going to have a phase shift, and that's what's really important here, is that because this reflection didn't travel as far as that reflection, they aren't necessarily going to be in phase with each other. So as I add all these contributions together, each one has a different phase shift in its sine wave because they've traveled a different distance. Alright? Now, you can actually sum this up. It turns out the sum converges to something nice, but we're not going to do that. We're just going to kind of take a little simpler picture here and say, when do I get bright reflection and when do I get not very much reflection? Well, the key is here, if all of these come out in phase with each other, I'm going to get a bright reflection. If they're if this one is 180 degrees out of phase with that one, which is then going to be 180 degrees out of phase with this one and so forth, that's when I get my minimum in reflection. Alright? So, for this class we're not going to worry about doing that sum. We're just going to say, when do I get a bright reflection and when do I get a minimum reflection? So when do I get a max reflection? I get a maximum reflection when the phases of those guys, the phase of this reflection and this reflection is the same. Alright? So what's the difference in phase from here to here? Alright? Well, if I look right here, this guy immediately gets a 180 degree phase shift because I'm going from low index to high index, right? So I want this one, if I want these to be in phase, I want this one as it travels this path to get a 180 degree phase shift, so it'll be in phase with that one. Or maybe 360 plus 180 and so forth, right? So how do I calculate the phase shift? Well, I get a 180 degree phase shift when my light travels half of a wavelength, right? So what we're going to do is we're going to say, remember, I'm drawing these rays at an angle just so we can see them. We're really imagining what happens at normal incidence. And for this class, we're just going to consider what happens at normal incidence. But if my film has a thickness T, what I want is, well, the light travels 2 times that thickness, right? It goes down and back. Once again, it's really going up and down. I'm just writing it at an angle so we can see. So the light travels 2 times that thickness, and we want that to be equal to, we said, if it were half a wavelength, that would get us 180 degrees out of phase, or 3/2 of a wavelength would get us, 2/2 would get us back in phase, and then another half gets us, matched to that one at 180 degrees. So we want an odd number of half wavelengths. So in other words, we want this distance to be m plus 1/2 times the wavelength of light. Alright? When that happens, we get maximum reflection. There's one caveat though. I mean, here's the equation you're going to use, sort of. But when the light is in here, it has a different wavelength than when it's out here. Right? I think we talked a little bit about when we had waves reflecting off of walls and things. The thing that stays the same for a wave is its frequency. The frequency stays the same, which means if the light slows down, the wavelength goes down. Right? Remember, wavelength is the speed of the wave divided by the frequency. Alright, we'll call this c in the medium. But the speed in the medium is the speed of light in vacuum divided by n, right? And so that means the wavelength in the medium is going to be the wavelength in air divided by the index of refraction, right? C over F is the wavelength in air. So let's call this in the medium, and let's call that in the air. So what we want up here is 2 times that thickness. We want it to be a half integer number of wavelengths in the medium. but the wavelength in the medium is the wavelength in air or in vacuum divided by n. Alright, so there's our equation. For maximum reflection, we want 2 times the thickness to be equal to an integer plus a half times the wavelength divided by the index of refraction. So there's one equation. There's when we get maximum reflection off of a thin film, like a soap bubble. Alright? When do we get the minimum reflection? Well, we get that when 2 times the thickness is going to be a full integer, right? So this wave reflects, gets a 180 degree phase shift. This one doesn't get a 180 degree phase shift. So if this distance is an integer number of wavelengths in the medium, I come out here, this will be 180 degrees out of phase with that one, and we'll get a minimum. So we want 2t to be m times the wavelength in the medium, but the wavelength in the medium is just lambda over n. So our equation to find a minimum is 2t equals m wavelength over index of refraction of the stuff. What is the index of refraction we care about? Index of refraction in here, because that's where it's traveling. If I had 3 different indices of refraction, like n1, n2, n3, when we calculate our wavelength, we care about the wavelength in this medium, not in this one, not in this one, because this is where we're getting our extra travel. So it'll always be that index of refraction that goes in right there. All right? But what would happen if, for example, I had air and then I had a little thin film, all right? And let's say this is water. So now I've got a little thin film of water, but let's say that that water is on top of glass. So my air has an index of about 1, water has an index of about 1.33, and glass, depending on the glass, you know, it'll be different, but let's say it has an index of 1.5. All right, now what happens is I get a reflection here. This reflection gets a 180 degree phase shift. When we come down here, this reflection, we're going from high index to even higher index, right? So that's low to high index. I'm going to get a 180 degree phase shift here as well. So when I have this case, if I want to get maximum, I want this to be an integer number of wavelengths because they both get this 180 degree phase shift. So when we talk about a soap bubble, these are the equations we use for maximum and minimum reflection. But if I, instead of going from low, high to low index, if I go from low to higher index, these two equations are going to swap. Same thing if I go from high to lower to even lower index. These two are going to swap. But for the most part, we'll be using these, but be aware, I may throw you a problem on an exam where we go from low to high to even higher, and then the equation that gives us minimum and maximum reflectivity will swap. Don't get caught off guard. Okay, now, notice, for a given thickness, this equation can be true for different wavelengths by changing m, right? M can be any integer. So for a given thickness, there are certain wavelengths which will have maximum reflection. So when you look at a soap bubble, you see these different colors, all right? In certain places, right here, the thickness is such that green reflects very nicely. But over here, green doesn't reflect so good, but blue does because the soap bubble doesn't have a uniform thickness. So the thickness is different. And that's why we see different colors in a soap bubble, all right? Similar thing when you see oil on water, right? You see the pretty colors. It's because of thin film interference. Another place where thin film interference shows up a lot is on lenses. If you buy a nice camera, or even a pair of eyeglasses, sometimes you'll notice that if you look at them, the lens looks kind of a funny color. It has kind of a tint to it. Why does it have that color? Well, that's because they put a coating on it to try and minimize reflection. So they've chosen, you can do this with one layer, you can just have your glass, and you can put a thin layer on that glass, and if you make that layer just right, you can minimize the reflections that happen at these two surfaces and get as much light as you can transmitted. A really nice lens will actually have a coating with multiple layers, where they put multiple layers down so that all of them together can really cancel out reflectivity very well. So you can get very low reflectivity and capture lots of light on your lens. And that's good because more light in your camera means, right, shorter shutter speeds, but even more so, if you have reflections off of the surface, it can make ghost images and make your image not as clear, blur out your image. All right, there's more than one path. The light, instead of having the light come straight in and making an image, it can bounce around and do other things. All right, now, a lot of bugs have really iridescent colors to them, right? You look at them and they have these pretty colors, and as you change the angle you look at them, the color changes. All right, now that's because this color, for example, in this fly is not made of something green. What it's made of is not green. Why does it look green? Because there are microscopic structures and different colors of light interfere differently, kind of like thin film interference, right? You look at your glass, the glass is not blue, but maybe a particular part of it looks blue because the thickness is just right to reflect blue, to make a thin film interference for blue that's very strong in reflection. The same thing's happening here. They have these microscopic little structures, these regular little structures, and when the light reflects off of, here and here, maybe that path difference is just right so that these two reflections add together in phase and you get a bright reflection for one color, but for other colors that have different wavelengths you get destructive interference. So the color of this fly does not come from a pigment, which is absorbing light. It's coming from microscopic regular structures, regular patterns that reflect light in such a way that some colors you get constructive interference and some colors, some wavelengths of light, you get destructive interference. All right? Same thing with the peacock's feathers. Why do the colors change when you look at it in different directions? It's because of these microscopic structures doing interference. So some colors interfere constructively and some destructively. And as you change the angle, right, the path length changes because, just like with our thin films, we talked, all of our calculations were assuming normal incidence. If you really came in at an angle, right, that path length changes and different colors will reflect constructively and destructively in different angles. All right? Fish, you get a rainbow trout or whatever this kind of fish is. You look at them, and as you change your angle, why is a rainbow trout called a rainbow trout? Because it's got these microscopic structures that make interference, like thin film interference. All right? Also, lots of crystals. You get a little oxide layer on bismuth, and depending on how thick that oxide layer is, it will reflect different colors, right? If you take a piece of steel, you may have noticed, I don't know if you've ever done an experiment where you get steel really hot and you start forming oxide layers, you can get kind of pretty colors in your steel from the thickness of the oxide layers doing thin film interference. Shows up everywhere. Beetles, same sort of thing. Now, there's a really cool video you can go and look at where they look at a butterfly, and in the video they actually change the angle and you can see the colors change slightly. Then you put some acetone on here. And the acetone, so you've got these microscopic structures, the acetone fills in the space in between. So instead of air, you've got acetone. Light has different wavelengths in acetone than in air, so it changes which colors reflect constructively, and the color of the wing changes when he puts the acetone on. When the acetone evaporates, it goes back to being blue. And here's another really cool video you can look at where they actually stamp microscopic little bumps, little holes into plastic and make pretty colors. The same idea, all right? Interference. Light is awesome and amazing. I hope you appreciate that. Okay, now why don't we see thick film interference, right? I've got my glass. I've got the glass window in my office. I can turn around and look at it and, no, I don't see pretty colors. Why don't I see pretty colors? Well, that's because what was our equation that tells us when we get pretty colors, when we get a maximum reflection for a particular wavelength? It's 2t equals m plus 1/2 times lambda over n, all right? If T is really, really thick, right, much, much thicker than any wavelength of visible light, then for a particular color to reflect strongly, M has to be really big, all right? So it is possible that for some particular wavelength of visible light, I can get a really bright reflection, but that will correspond to plugging in a pretty big M in this equation, all right? The point is, for really thick glass, if I change M by 1, I only have to change the wavelength by a little bit. If I have a really big M, and I change, if M is 1, and I change it by 1, I go from M equals 1 to 2, that's a big change, a big, change in this parameter here, which means I have to have a big change in the wavelength. But if M is 10,000, and I change it to 10,001, I've only changed this by about a part in 10,000. Right? Which means I only have to change my wavelength by a part in 10,000. So if I have a thick piece of glass, like here I've simulated a microscope slide and I'm shining light on it with a wavelength of 650 nanometers. My microscope slide is slightly wedged so that the red light I get nice reflections in certain places, but I get a minimum in other places where the thickness isn't quite right. But the point is, if I look at this fringe right here, that corresponds to an M that is really big because my microscope slide is very thick compared to the wavelength of light. So it turns out if I change the wavelength of my light a little bit, where these maximas occur will be different, right? If I go to my equation, if I change the wavelength a little bit, I have to change the thickness a little bit to keep a maximum reflection, all right? So I change the wavelength a little bit and these move, all right? So I'm putting in different wavelengths. Now, why didn't I make the color different in my simulation when I change wavelengths, right? We know that color has to do with the wavelength of light. The point is I'm only changing the wavelength a little bit, all right? So if I have a thick film, right, if this wavelength is making constructive interference right here, a very similar wavelength is making constructive interference here, and very similar ones making constructive interference over here. So kind of all these different wavelengths of red reflect brightly in different places, but they all look like the same color to me, so I don't see the nice fringes anymore. I don't see the interference anymore, all right? So for any thickness, there is some wavelength of red that looks the same to my eye that's going to reflect brightly, so they all wash out together. However, if you take a thick piece of glass and shine a laser beam so that there's only one wavelength, then you will get the stripe patterns that you expect to see from thin film interference, even with thick films. When you work in a laser lab, anytime a laser goes through a piece of glass, you get this kind of interference. It shows up all of the time. All right, so that's thin film interference. What is it good for? Practical uses of interference. We talked about this, I think, a little bit with waves, but interfering sound with sound, you can cancel out noise. I discussed anti-reflective coatings on lenses. You can also, instead of taking a lens and trying to make it as little reflection as possible, you can also put stacks of thin films to make extremely reflective mirrors, mirrors that reflect really, really well. You know, a piece of aluminum, it reflects something like 90-something% of the light. I have mirrors in my lab that reflect 99.999% of the light because they have multiple thin films on them designed to be very reflective. You can also make selectively reflective mirrors. I have some mirrors in my lab that reflect red light but not blue light, and they have thin films designed to reflect one but not the other. All right, it turns out that holography is a type of interference. By catching the interference of something, you can make a hologram. Phase contrast microscopy, it turns out you can use interference to make invisible, to make transparent things suddenly become visible without staining them. So you can get a microscope, you can put an amoeba in there and see the amoeba even though it's clear. All right? Another use of interference is interferometry, and we're going to talk about interferometry because that's my bread and butter these days. All right, so the first optical interferometer of renown was made by Michelson and Morley. They were using it to try and figure out how light traveled, and it turned out that their discoveries, or their lack of discoveries, are what resulted in the special theory of relativity, and we'll talk about that when we do modern optics. But for now, just understand this is how an interferometer works. This is when we do modern physics. For optics now, we're just going to understand how this works. So imagine I have a laser beam. They didn't use laser beams, but same idea. Some beam of light. It comes in and it hits this thing, which is we call a beam splitter. A beam splitter is something that's partially reflective. A piece of glass can be used as a beam splitter. Some of the light transmits, some of it reflects. All right. So I've got this beam splitter. It reflects some of the light. It transmits some of the light, and my light goes on. It hits two mirrors, bounces off the mirrors, comes back to the beam splitter, and then comes out. Right now, the light that was going this way, when it comes back, some of it goes this way, and some of it reflects. The light that went this way, some of it reflects, and some of it transmits. So the light that's coming out here is a sum of light that went this way and light that went this way. All right? And when I add those two together, I get interference. Now, if the two waves are in phase, I'm going to get constructive interference, and I'm going to get a lot of light coming out of here. How would I get them to be in phase? Well, imagine, if you will, that these two distances are exactly the same. Then they would come back in phase. But if I move one of these mirrors a little bit, that will delay this light. It has to travel a little bit further, so when this beam comes here, it'll be a little bit out of phase with this one. If I have two beams that are a little bit out of phase, all right, I add them together, and I still get some light, but it's not as much. If they're 180 degrees out of phase, I get nothing. All right, so with an interferometer, how much light I get coming out here depends on these two distances. All right? Now, how far do I have to move this mirror to go from getting all the light coming out here to getting no light coming out? Well, I want this path to be different from this one by half a wavelength. But since it travels out and back, that means I need to move this mirror by 1/4 of a wavelength, and that will result in going from bright to dark output. All right? So the great thing about an interferometer is, what's the wavelength of light, of visible light? It's like half a micron. If I move 1/4 of a half a micron, my signal goes from really bright to essentially nothing. So I can get big changes in what I'm measuring with very small changes in motion. So you can use a Michelson-Morley interferometer, you can use an interferometer to measure very precisely how things move. People do this to measure just very microscopic motions of things, for example. All right? Or you can put something in here, rather than moving the mirror, you could put something in here that changes the phase of the light. For example, you will do a lab where there's a little cell, and you can replace the air with helium, or you can replace the air with vacuum, and see how that changes the phase. And you can use that to measure the index of refraction of air and helium. All right? You can do it extremely precisely with interferometers. Interferometers can make really, really precise measurements. All right? So how much do I need to move a mirror to go from a bright fringe to a dark fringe in an interferometer, in a Michelson-Morley interferometer? 1/4 of a wavelength. How much to move from a bright fringe to a dark fringe and back to a bright fringe? That's going to be half a wavelength of the light. So, because light is a wave, we can make interferometers, and because light has tiny wavelengths, these interferometers can be extremely sensitive. What are they good for? You can use them to identify atoms and molecules. So an atom gives off some light, you send it into an interferometer, you can very, very precisely measure the wavelength of the light by scanning one of the mirrors and seeing how far you have to move the mirror to make, the fringes, to make it go bright and dark 20 times or something, and then you can calculate the wavelength of the light. You can measure rotations, all right? There's another type of interferometer that's pretty common called a Mach-Zehnder interferometer, where instead of sending the light back to your first beam splitter, you reflect it to a second beam splitter. Now imagine this whole thing is rotating. You look at how much light's coming out here. All right, this light comes, but because your whole experiment is rotating, by the time they get to this beam splitter, the beam splitter's moved a tiny bit. That changes the phase, changes how much light is coming to your detector. So if you get on a 747 and fly to Hawaii, the plane needs to measure how it rotates, right? But instead of having a mechanical gyroscope to help you do that, they will have a Mach-Zehnder interferometer where they send light around two different paths and measure their interference to see how the plane is rotating. All right, you can measure tiny, tiny movements. I mentioned if that mirror moves a little bit, there's a thing called a laser microphone, where if you're up to some big conspiracy, the FBI might come and shoot a laser beam at your window and use interferometry, use a Michelson-Morley interferometer to measure the very tiny vibrations of your window that are caused by your voice, and they can listen in to what you are talking about. The world's largest Michelson-Morley interferometers are part of a project called the LIGO project. They have 4-kilometer long arms in their interferometers. So they got a laser, shoot the laser to their beam splitter, and then it goes out 4 kilometers before coming back. And then they do all kinds of other crazy things to make it even more precise. And they're hoping they can actually see ripples in space-time itself. So, a black hole collides with another black hole, a neutron star explodes or something. I don't know. Neutron stars collide. They make these tiny, tiny ripples in space-time, and they're looking for those using a giant Michelson-Morley interferometer. Precision spectroscopy, measuring the wavelength of a laser very precisely, measuring the wavelength of light coming from a star or from an atom very precisely. You can use interferometry to characterize optics. This is an experiment I had one of my students do, measuring kind of the angles between surfaces on precision optics using interferometry, and she was able to do it with microradian precision, microradian small. Take a meter stick, move one end of it by 1/1000th of a meter, and you have rotated it by microradian. All right, when I was a postdoc, I worked on a cesium interferometer. It turns out when we study modern physics, we will learn that atoms and, well, basically everything behaves as a wave, so you can actually make an interferometer with atoms where you make the atom's quantum wave interfere, and that's what I did as a graduate student. I mentioned, how you can use an interferometer to measure rotations in an airplane. We made a much more precise gyroscope interferometer using cesium atoms rather than light waves for our waves. And right now in my lab, we're working on trying to build an interferometer that uses the quantum waves of strontium ions to try and measure electric fields with unprecedented precision. Anyway, interferometers are dandy, but we're done.